Are you thinking about buying an electric vehicle and wondering what you should really pay attention to? Then this video is for you. We asked the question, how fast does a car actually need to go in order to reach its destination as quickly as possible? For a combustion engine car, the answer is clear: as fast as possible. For electric cars, that is also true on short trips. But on longer trips, higher speeds mean more charging stops for an electric car. And every charging stop costs extra time. Is there an optimal speed? And what does a larger battery actually achieve? Welcome to Physics with Lucky. Today we are talking about the physics of electric cars. We derive the optimal cruising velocity and explain which vehicle properties actually affect travel time. We then compare several popular electric vehicles based on these properties, and at the end there are even a few car buying recommendations from the physicist and his cat. As so often in physics, we start with an idealized model that still contains enough realistic aspects to give us a meaningful result. Our first simplifying assumption is that the vehicle moves at a constant speed throughout. So we are in the regime of uniform motion, which we looked at more closely in our last video. Of course, that is not exactly what happens in reality, but for now we can neglect it. What we cannot neglect, however, are air resistance and rolling resistance, both of which oppose our attractive force. We then assume a battery with a maximum usable capacity EBUT and an average charging power PC. Both are realistic assumptions, so they do not add further restrictions to our model. However, we neglect charging losses. That is not a problem because we can simply reduce the average charging power by the charging losses. We also do not include the extra driving time to and from the charging station. That is only a minor limitation, especially if the charging stations are located directly at the highway service areas. If needed, the model can easily be extended to include this effect. We also restrict ourselves to a flat route without hills or equivalently assume 100% recuperation efficiency. Our drivetrain also has 100% efficiency, which is actually not too far from reality for electric cars. So, our largest deviation from reality is the assumption of constant speed. Therefore, our results apply best to a steady driving style with an average speed and only small deviations above or below. We will now proceed as follows. First, we derive a function for the travel time as a function of velocity. Then we take its derivative and set it equal to 0 to find the minimum travel time. Finally, we solve the result for v and obtain the optimal cruising velocity. The first part will take the most time. First, we need an expression for the attractive force. For this, we begin with the velocity. The velocity is equal to the average velocity and, as mentioned, it is constant. That means its time derivative is equal to 0. Since the time derivative of the velocity is the acceleration is also equal to 0. Of course, if we assume a constant velocity, there is no acceleration. Newton's second law then becomes very simple. The sum of all forces acting on the vehicle is equal to the mass of the vehicle times the acceleration, and is therefore also equal to 0. Here, the x direction is our direction of travel. So, which forces act in the direction of travel? First, there's the tractive force from the motor. We mark it here with a small circle or wheel. Acting against it are the air resistance Fd and the rolling resistance of the tires on the road. For the car to maintain its velocity, these forces must cancel exactly. Their sum is therefore equal to 0. We can now move the two resistance forces to the other side of the equation, and there we have our expression for the tractive force. In the next step, we want to calculate the tractive power. For that, we need to make the expression for the tractive force a little more specific. Let us start with the rolling resistance. The rolling resistance is the product of a rolling resistance coefficient, Cr, the vehicle mass, and the gravitational acceleration g, that is 9.81 meters per second squared. The rolling resistance coefficient is a measured quantity And of course, it takes different values for different combinations of tire types and road surfaces. These values can be looked up in tables. Air resistance is the product of air density, the vehicle drag coefficient CD, the frontal area of the vehicle A, and the square of the velocity. So the faster you drive, the greater the air resistance, and the thinner the air, the smaller the resistance. In Mexico City, for example, at about 2,240 meters above sea level, air resistance is about 20% lower than on a road at sea level. So by choosing where you live wisely, you can save quite a bit of electricity. Our tractive force was the sum of Fr and Fd. We can now write these out explicitly. The tractive power we are looking for is tractive work per time. And the tractive work is the tractive force times the distance traveled. And since distance divided by time, that is s divided by t, is the velocity v, we are left with p is equal to f times v. We can write this out and obtain the tractive power required to balance the resistive forces at a given velocity v. This is usually given in kilowatts. Notice the important dependency on velocity here. The rolling resistance part grows linearly with velocity, but the air resistance part grows with the third power of velocity. So if you drive 10 times faster, the power you needed to overcome the air resistance increases by a factor of 1000. That is why high velocities are so expensive for electric cars. Speaking of units, we want to make a short detour here, because kilowatts and kilowatt-hours are often confused. Here again is the definition of velocity. Total distance s divided by driving time t, and the rearranged version solved for the time. Tractive power is the tractive work divided by travel time. Therefore, tractive work is tractive power times travel time. In our equation for power, we eliminated the time by substituting the second equation, just as we are doing here for the work. By the way, we will need this equation twice in the next step. The fact that time no longer appears explicitly here does not change the fact that time is the key factor connecting work and power. And so we come to the units. The SI unit of work is the joule. However, it is rather inconvenient and is usually not used in the context of vehicles. Instead, we use the kilowatt-hour, which can be used equivalently to the joule. 1 kilowatt-hour corresponds to 3.6 megajoules. Energy has the same unit. The energy content of a battery is also given in kilowatt-hours. With this energy content, exactly the same amount of work can be performed. If you ask me, energy and work are basically the same thing anyway. But Lucky insists on using the exact terminology. Power, on the other hand, is work per time. Strictly speaking, joules per second or kilowatt-hours per hour. Nobody says it like that, of course, even though it might actually be clearer. Usually the hour is cancelled out, leaving the kilowatt. Unfortunately, it is not longer immediately obvious from this unit that this is a unit of power, and that is why kilowatts and kilowatt-hours are often wildly confused. I have even seen the unit kilowatts per hour, but that has no meaningful use in physics. Okay, so much for the units. Now we finally come to the travel time. In general, we can say that the travel time is the sum of driving time, which we call t-circle, and charging time, which we call tc. That is all you do on such a trip. You drive or you charge. And if you have other needs, you can take care of them during the charging time, right? To determine the driving time, we take the definition of power and simply solve it for t. We can do the same for charging time. The charging power is the total energy that has to be recharged divided by the total charging time. Energy is the ability to perform work and therefore has the same unit. As I said, for me it's kind of the same thing. Now let us insert this on the left. The tractive work W was P times S divided by V. So we can insert that directly in place of the fraction on the left. On the right hand side, we need an expression for the energy EC that has to be charged. So how large is the total amount of energy that needs to be charged? It is the work W required for the entire trip, minus the amount of energy already stored in the battery at the start of the trip. Since it is reasonable to assume that the battery is fully charged before the trip begins, this stored energy is exactly the usable battery capacity. The tractive power P on the left can therefore be cancelled for the moment, and on the right we split the numerator apart. We replace the remaining tractive work W by P times S divided by V, and obtain our final result for the travel time. The three terms in this function are easy to understand. The first is the pure driving time. The second is the charging time for all the tractive work required, and from that we subtract the time that we already spent before the trip to fully charge the battery. Beautiful, isn't it? That completes the first step. By the way, we will plot the function t of v later in a graph. Now for step 2. To determine the optimum travel time, we have to take the derivative with respect to v and set it to 0. Let us write down t as a function of v again. Pay attention to the expression p divided by v. Earlier we determined p by multiplying the tractive force F by v, so if we now divide p by v, we are simply left with the tractive force F again. So we insert that. And now we take the derivative with respect to velocity. S divided by v becomes minus s divided by v squared. The rolling resistance term contains no dependency on v, so it is a constant and disappears when we take the derivative. The same is true for the charging time at home. The only term left is the air resistance term. When we take the derivative, v squared becomes 2 times v, and the factor 1/2 cancels the 2, leaving just v. If we expand this, we obtain the desired derivative. So now we set this derivative equal to 0 and solve for v. As the first step, we move s divided by v squared to the left-hand side. And then we divide both sides by the distance s. In the next step, we do two things. We multiply both sides by the charging power Pc and by v squared. Then we solve for v cubed. And finally, we take the cube root. Done. What a beautiful compact result for the ideal cruising velocity. But now let us look at what the ideal velocity depends on and what it does not depend on. We immediately see that the battery capacity does not appear at all. Who would have thought that? The decisive quantity in addition to the charging power, which should be as high as possible, is the product CD and A, also called the drag area. This value should be as small as possible if the velocity is to be high, or if the number of charging stops is to be low. Let us now look at a few examples of popular electric vehicles. The table is sorted so that the drag area increases from top to bottom. In other words, it gets worse. The differences between the top models and the last entry in the table are already quite large. By the way, you can find the sources for the values in the video description. However, some values depend on the exact version of the model, and most frontal areas are actually estimates, because many car manufacturers do not provide them directly. So what does this look like in detail? In the diagram, we have plotted the optimal cruising velocity as a function of the average charging power for 5 different models. For the air density, we used 1.225 kilograms per cubic meter, the value at sea level, not the value in Mexico. For example, you can see here that for none of the models does it make any sense to drive faster than about 65 miles per hour if you can only charge at 11 kilowatts during the trip. Fortunately, those days are mostly over. At 22 kilowatts, a Xiaomi SU7 Max already has a reasonable cruising velocity of about 80 miles per hour. With an ID4, you reach your destination fastest at just over 60 miles per hour. With modern fast chargers, average charging powers above 100 kilowatts are often achievable. In that case, it can make sense to drive above about 95 miles per hour with all of these models, provided the cars allow it. For the top models, even more than 120 miles per hour can be reasonable. On public roads, however, that is mostly a German Autobahn privilege. Lucky would like to point out once again that these results only apply under the idealized conditions on which our model is based. In reality, these values are of course lower. We now want to plot the travel time as a function of velocity once more, using the Tesla Model 3 with a usable energy of 75 kilowatt-hours as an example. Here we have one curve for each average charging power from 11 to 150 kilowatts. For a distance of 30 miles, all curves are identical. The travel time decreases as velocity increases, and the ideal velocity is the maximum velocity because we do not have to recharge on such a short trip. As the driving distance increases, it becomes clear that there's ultimately always a velocity above which the travel time becomes longer again if you exceed it. This point is different for each charging power. The Tesla should usually achieve an average charging power of 100 kilowatts or more, in the range from 10 to 80% battery charge. So in our idealized model, an average velocity of 124 miles per hour would indeed be ideal. By the way, you do not have to fully charge the car. Since the charging power drops significantly as the battery state of charge increases, it is even sensible to stop charging as soon as the charging power falls below 100 kilowatts. You then have to return to a charging station sooner, but driving to and from the charging station costs no additional time. At least that is how we defined it at the beginning. Okay, let us summarize our results once more. The tractive power for the entire trip is given by the sum of the resistive forces multiplied by the cruising velocity. The travel time was the driving time plus the charging time minus the charging time before the start of the trip. And the formula for the ideal velocity depends essentially on the vehicle's drag area and the average charging power, but not on the battery size. And now we come to the recommendations from the physicists you trust and his cat. Let us distinguish between everyday driving and longer road trips. As far as the vehicle's drag area is concerned, it hardly matters for everyday driving. You are simply driving too slowly for that. On longer trips, however, it is an extremely important quantity, so Lucky would make sure that this value is as small as possible. When it comes to battery size, it strongly depends on whether you have your own home charger or not. If you do, then a battery with an energy content of 30 kilowatt-hours is sufficient. The assumption is a daily driving distance of about 25 miles. In that case, the car would have to be plugged into the charger about every 2 days. However, if you have to rely on public charging, you may want to do that at most once a week. In that case, Lucky would recommend at least 65 kilowatt-hours. That is also the minimum value for longer trips. For the charging power, the recommendation also depends on whether you can charge at home. If you can, then 11 kilowatts is enough. Overnight, that will fully charge almost any battery. Otherwise, this value should be as high as possible. This is really important. Especially on longer trips, you do not want to spend forever at highway service areas. It should be at least 100 kilowatts. And with that, we end the video for today. If you want to see more about electric vehicles, let us know. Lucky would be happy to explain the rules of thumb for range and charging times, or to derive a more detailed model for the ideal velocity with even more realistic assumptions. But first, he has to recover after losing a fight with the neighbor's cat, so wish him all the best.